So here we have a notice in the beginning that the students can leave their email. Essentially, what you need is to leave an email. And then I will create exam questions. They will be personal for everybody who leaves this email. Here is the form you have to fill. After you fill the form, you will receive the questions, and you can check this page for updates if you didn't receive something, or send me email. Okay, this is about the exams which will occur sometime next next week I will send the, so the exam will be just you get problems and you solve them. That's the exam. And then you tell me in person how the solutions. So for people who cannot go to exam in person, they are not supposed to get a grade. They are supposed to get some notice that they have completed the course, and that's it. This is what IMPA in Sino told me. Okay, so today I will speak about smooth manifolds, well, smooth points and algebraic varieties, and what is this something we have discussed a couple of lectures ago, but what I will explain the algebraic side of this picture, which is it's a property which is called regular. So smooth points on algebraic varieties correspond to regular local rings. Okay, so there was a couple of things which we had discussed last time. So first you have, if you have an ideal inside a ring, then you can take associated graded ring, which is a direct sum of I power k for k equals 0 to infinity, quotient by I k plus 1. So here I use convention I power 0 is A. This is associated graded ring. So, yeah. Unless you have a question, so I will go on. And what we did, there was two theorems which were proven. The first, that if A star is finitely generated, it's a graded ring which is finitely generated, then dimension an is polynomial function on n. N for n sufficiently big. And second theorem is that this degree, so let's call this called Hilbert function. Let's call it h a of n. So degree of this polynomial is equal to Krull dimension of R, if R is a local Noetherian ring and A it's associated graded. Well, in particular, this implies, since associated graded is already graded, its associated graded is itself. So this implies in particular that the Krull dimension of A star is equal to Krull dimension of R. So the passing to associated graded ring doesn't change the Krull dimension of the ring. This is what we had last time. This observation wasn't stated last time, but we will need it today, so I repeat it. The rest was done. Everything is fine? Good. Okay, so the key notion today is the notion of regular ring, which is pretty much the same as the smooth points on varieties correspond to regular rings in regular local rings in the commutative algebra. So I will start with a theorem. It's a theorem defining essentially what we give you three properties which are all equivalent and they all define regularity. So suppose you have R, a regular local ring, the crude dimension is D. Then, and I also assume that R, it's a notation. It's regular local ring. Sorry, not regular, Noetherian, of course. It's Noetherian local ring, dimension of R is equal to D, and K, this is a field, it's R quotient by maximal ideal. M maximal ideal. Then, dimension of maximal ideal quotient by its square is bigger or equal than D. And moreover, the following are equivalent. Okay, so the first condition is that you take the associated graded ring. Let's call it GR of R, associated graded ring, is polynomial. So it's equal to K of okay, I need to write A1 because I have this notation on the slides where A1 is the first, so A star is this associated graded GR star of R. And this is the first component of the associated graded ring. So this is, in other words, A1 is maximal ideal by its square. Okay, I will write here. The second condition is that the dimension of this space, A1, of M quotient by M square, of course, it's the same as on 1 as D. By this first statement, it's no smaller than D, and the condition is that it is exactly D and not bigger. And the third condition is that M, the maximal ideal, is generated by D elements. Okay. There are several observations which are entirely clear. For instance, first let's start with the inequality. Yeah, so the first implies the second is clear because look, this graded ring, which is polynomial, has dimension n because polynomial rings have dimension the same dimension as this number, because polynomial rings have the same dimension as polynomial rings C k of k of T1 to Tk is equal to k. And then by this observation, we know that dimension of this associated graded ring is the same as dimension of R, which is D. So if it is polynomial, the number of generators is precisely D, no more, no less. So this is how the first implies the second. Now the second implies the third. This is because if you have any set of generators which generate m by m squared, they generate m. This is Nakayama lemma. If you have generators up to m squared of any model, in fact, if a1 dot an generate m modulo m, where m is maximal ideal of a local ring and m big is any finitely generated model, then ai generate m. This is Nakayama. Okay, so this gives you implication 1 goes to 2, goes to 3. It's free. There's nothing to do. Okay. Also, what we have is that A is a quotient of the polynomial ring of A1 by some ideal. This is because this graded ring is generated by A1, essentially by the same property. If you have a finitely generated model over a local ring, it is generated by any set of generators which generated up to a maximal ideal. So A is generated by this space, then it is a quotient of polynomial ring because any ring which is generated by a finite set is a quotient of polynomials generated by the same set. Okay, and then dimension of, suppose let's write dimension of A1 is equal to K, then dimension of A is less or equal than K. And in fact, equality happens if and only if this is equivalent to I is trivial. This first, dimension of polynomial ring is K. And if you take a quotient of polynomial ring by any polynomial, which is non-zero, you immediately obtain a smaller dimension because tensorial dimension is smaller. And we know that cool dimension is equal to tensorial dimension, at least for finally generated ring over a field. This we know. So I equals 0 if and only if the dimension of A is equal to K. But then this is D by this observation. And this, we just proved that D is smaller or equal than dimension of A1. This is the first observation of this theorem. This we proved, right? And clear? Okay, the next we need to prove 3 implies 1. And that's, then we are done. So how to see that 3 implies 1? So this is step 2. 3 implies 1. Okay, there is pretty much nothing to prove because if this maximal ideal is generated by D elements, then the ring is generated by D. Well, if this maximal ideal is generated by D elements, then it's then if this implies, so 3 implies that A is a quotient of a polynomial ring K of T1 dot Td, which are the representatives of, well, it's the classes of the generators modulo m squared. So they also generate. If they generate up to modulo m squared, obviously. And it is quotient by some I. But as we just observed, since you have D here, the quotient has dimension less than D, and this dimension is equal to D if and only if I is 0. And we know that dimension of A is equal to D by this formula. Okay, then I is trivial. And this implies that this associated graded ring is a polynomial ring. Was I clear? Do you have any questions, comments? Should I repeat anything? Was it completely clear? No? Well, it's sort of easy. Look, you have your maximal ideal is generated by D element. Then they generate maximal ideal up to m squared. And this means that they generate A1. And then the ring A, which is generated by A1, is polynomial up to some ideal I, and you have at most D generators, because the D is a number of elements generating maximal ideal. So it's a quotient of polynomial by I. Now, what is its dimension? Dimension of polynomial ring is D, and if I is non-trivial, it's smaller. But dimension of R is equal to dimension of A. So this is the dimension of this ring is D, then I is trivial. And this means that A is polynomial ring, and this is what we need. Yeah, there are no relations. It's a free ring. Any more questions? Can I repeat anything? Is it entirely clear? So I can state briefly what happened. So if you have the condition is optimal condition is that the associated graded ring is polynomial. And then its dimension is equal to this space. A priori, this could be bigger, because you could have relations between elements in A1. But if it is, there are no relations, the dimension is the same. And in that case, of course, it's generated by D elements. So the number of generators for M up to M squared and number of generators of M is the same by Nakayama, as I wrote here. Okay. So this has theorem 3. At some point I will refer to it. Before I go, let me give you a couple more definitions. So definition. Noetherian local ring. Local ring is regular if these properties 1 up to 3, which are obviously equivalent, are satisfied. So it's D-dimensional ring with associated graded polynomial. Noetherianity is necessary For instance, if you consider the ring of smooth functions, localize it in 0, C infinity of Rn, localized in 0. So what is the maximal ideal of this ring? It's functions which vanish in 0. And then you can check that this ideal, so maximal ideal of 0 of this ring, is in fact is generated by coordinate functions, T1, Tn, coordinate functions. This follows from what is called Hadamard lemma, which states that if f for each function f, f is equal to some ti, gi, where ti is our coordinates, plus f of 0. It's for all smooth functions. So gi and f are smooth functions. So this means that our ideal M is equal to C infinity, is generated by T1 dot Tn. Okay. Then M squared, for the same reason, is generated by T2, T1, Ti, Tj, and so on. Like M third is generated by triple products of coordinates and so on. And this means that each subsequent quotient is in fact, so mk over mk plus 1 is symmetric, is polynomials of degree k up to polynomials, so it's a homogeneous polynomials. It's homogeneous polynomials of the generators of the coordinates. And this implies that the graded ring, associated graded ring of the smooth functions, is equal to polynomial ring. Well, it would be real if we are interested in real functions, and complex if we are interested in complex functions. So maybe I should write R, because most people do real functions. Okay, so this is regular, but it's, well, it would have been regular if we didn't ask for noetherianity in the definition. But since we do, this is not regular. Still, it is nice, and in fact, what you can do, you can try to look at, well, you can look at functions on a space and try to define smoothness, and then you can, this would be a good approximation of smoothness for more general situation. This is something we shall discuss in the end. Okay. Now we have this integral closure of a Noetherian ring. This is something I'm going to skip, in fact, because today we have too much material I wanted to present, and we won't have time for everything. So I would skip the next slide and part of this particular slide, but let's do something for dimension 1 at least. So what happens in dimension 1? Yeah, and before that, we can also define smoothness. Now we can define smoothness in algebraic language. So definition, you have affine variety A in Cn, are fine. Then you have for each, it's called smooth. If for each x in A, the local ring, localization of the ring of functions in the maximal ideal of x is regular. And also, this point is called smooth if it is localization is regular. This is the first observation. Of course, we didn't yet prove that there exists at least even one regular point, but this would follow in the end because I will indicate how to you interpret this condition in terms of the smoothness condition which we discussed a couple of lectures ago when we had this complex analytic discussion. Okay. Now there's a trivial claim. So if you have R as discrete relation ring, then R is regular. Proof. Well, the maximal ideal of R is principal. And we use this the third condition. In the definition, we says that if your ring maximal ideal is generated by D elements where D is dimension, then it is regular. D is 1. And then you can have it for arbitrary Dedekind rings. So if you have a ring A, crude dimension 1, a ring of crude dimension equal 1 and Noetherian, then A is regular. Well, all localizations, all localizations of A are regular if and only if A is Dedekind. Or this is because local rings have dimension 1, and then they are regular if and only if discrete relation rings. But what is Dedekind ring? It's a ring which all localizations are discrete relation rings. And in fact, I won't give you this lemma because this lemma is technical. It's used to prove the next theorem, which I'm not going to prove ever. Sorry. But I would give you the statement, and then you can do it as an exercise or look at my slides later. So proposition. Suppose you have R is Noetherian local ring. Local. And GR A is associated graded. And suppose that it has no Z divisor. Has no Z divisors. Then the same is true for R. R has no Z divisors. The converse is false, as we had last time. Last time I gave an example of a ring which has no Z divisors, but its associated grade it has. Moreover, GR R is integrally closed. Well, if GR R is integrally closed, then R is also integrally closed. And this has an obvious corollary that regular rings, local rings, are integrally closed. Okay, why it is so? We know that regular associated graded ring of a regular local ring is polynomial. Then it satisfies assumptions on this proposition. It has graded, associated grade has no Z divisors, and it is also integrally closed. Then R is integrally closed. This is why if you have a regular ring, it is integrally closed. So in fact, if you remember the Dedekind, one of the definitions, well, it was a property, but you can use it as a definition. Of Dedekind rings, what that it is integrally closed, dimension 1. Then all its localizations are integrally closed, dimension 1, and for local rings, integrally closed of dimension 1, integrally closed is the same as discrete relation ring. So then this is what we have on that in that setup. You can think of, if you think of dimension 1 spaces as of complex curves, one-dimensional algebraic varieties, then it says that normality, integral closedness, is equivalent to smoothness. Because smoothness is Dedekind condition, and Dedekind is equivalent to normality. But this is more, it's for all dimension, that you know that from regularity, it follows that if your ring is regular, then it is integrally closed. Converse is false. Let me also give you an example of something which is integrally closed but not smooth, not regular. So an example is this is probably something we don't need anymore. So we're interested in this interesting variety C square quotient by plus minus 1. We have discussed that. So taking quotient by plus minus 1 is equivalent, this is something we proved, that this is equal to spectrum of polynomial functions T1, T2, which are invariant under G, where G is plus minus 1, acting T1 goes to minus T1, T2 goes to minus T2. This is true for any group. If you have a group acting on a space, then you can take the ring of invariants. It will be the same as the ring of the quotient. So passing to quotient is the same as of varieties is the same as taking invariants for the finite group. Okay, but we know what is this. This is the ring of even polynomials, right? So it's polynomials of even degree. So it's this ring C of T1, T2 is the same as C of X, Y, Z, quotient by X, Y is equal to Z squared, where X is T1 squared, Y is T2 squared, and Z is T1, T2. It's not hard to see that. Sorry? Yeah, thanks, of course, thank you. Of course, thanks. This is an exercise. But what is also important is that when we pass to invariance, you will always, your condition of integral closeness will be preserved. This is because if you have a, well, it's an exercise, but maybe I can improvise the solution. So if you have a monic polynomial P of t equals 0, and t, we want to say that t is invariant, is G-invariant, you can take project P of t to, you take P of t plus, we have our group generated by plus minus 1, so let's tau is generator, so this is tau, plus tau of P of t. This is also 0, so, and this is clearly the sum is a monic polynomial. So this means that if your t is the root of monic polynomial, it's a root of monic polynomial with invariant coefficients. So since this ring is integrally closed, the ring of invariant is also integrally closed. Because if you have something inside the ring of invariance, and it is, I mean, it's a quotient of two regular functions, but it's a root of monic polynomial, it will be root of monic polynomial inside here. Okay, so, yeah, but it's not smooth. Look, it's two-dimensional, right? Well, it's something, if you have a finite map, the dimensions stay the same. And this is, so this thing is a quotient of C squared, so it's two-dimensional. But then it's two-dimensional, but its maximal ideal is generated by 3 elements. So if you look at the maximal ideal, it's generated by X, Y, and Z. So its quotient by its square is 3-dimensional. It cannot be smooth. This is an example of a space which is normal. Normal means that it's integrally closed. It's a ring of functions integrally closed, but not smooth. Okay. What I'm going to say now is to connect this algebraic side of the story, which we developed, with the geometric side, which was a couple of lectures ago. In the end, I want to explain that regularity is in fact equivalent to smoothness, in the sense that we have, I mean, we spoke about smooth varieties, but we defined it in terms of analytic, complex analytic, in terms of analysis, essentially. We said that, okay, variety is smooth, it's locally there is local diffeomorphism or biholomorphic diffeomorphism to something smooth. And I want to have a purely algebraic version of the same notion, and I will tell you that why the regularity is this purely algebraic version. So The name Scalar Differentials is quite funny. I didn't have time to show you the, but you can read the referee report, the review in Math Reviews for the book of Scalar. Erich Scalar was a great geometer who is responsible for lots of differential geometry, the notion of Scalar manifolds and so on. Really great one. But he also, at some point, decided to do algebra, and he wrote a book on algebraic geometry. But since he never read the current literature, he used a very strange terminology. In fact, he took all terminology from philosophy and political science. Like ideals, homomorphisms, they're all very strange names. But still he did something. In particular, he defined what is now called Scalar differentials, and this is just differential of functions. But he did it very functorial way, which is more convenient than what people had at the moment. And I don't think he did much algebra after that. It was also published in Italian. Not, I think most people didn't like this book, but at least this notion of Scalar differential stuck. Okay. So the idea is that you can define vector fields as derivations. But vector fields are bad. They are not functorial. And then you can define this notion of Scalar differentials, which are very nice and functorial, but they entirely miss the point for smooth manifolds. If you define that for smooth manifolds, you will fail. You will obtain something horrible. So when people do smooth manifolds, if we are interested in algebraic side, they do vector fields and derivations. But if you want to work on algebraic geometry, you have to take duals, to derivations which are Scalar differentials. Okay, this was the side story about Scalar differentials. Now let's give, well, I will give you two definitions, derivations, definition. So you have a ring R. Typically, we will work over a field. So you can take differentials over a field, derivations over a field, or just derivations. So derivation is a map from R to some R model. M is R model, such that delta of xy is delta of x times y. This is element of R model. You can multiply it by y plus x times delta of y. This is Leibniz identity. So this is Leibniz. And then delta is called derivation or differentiation. Usually people assume that you work over a field and delta is k linear. No, not really necessary. For instance, you can prove that all derivations of algebraically closed field of transcendental dimension 0 are trivial. So for fields, derivations are interesting because they capture the transcendental parts, but since you never like to work, unless you are a specialist in mathematical logic, you almost never work for fields which are much different from closure of algebraic numbers. So when you do work with C, you always think, okay, everything which is true in C is also true in Q bar. So people always assume that differentials are k-linear. And the same with the Scalar differential, which is, yeah, and of course this is this model of derivations from k to v or to m is also a k model, R model. So from R over k is R model. These vector fields. In fact, you can prove it's a nice, very nice result, and just for smooth manifolds, the derivations of smooth functions on a manifold is the same as vector fields on this manifold. Now the Scalar differentials. So you see, here I already do k-linear stuff. Definition. you have R filled ring over K. So in all applications, we have rings over C. But you can do other. Yeah, you have R model denoted by omega 1 K of R. It's called model of Scalar differentials. It's generated, formally generated by elements df, where f is an element of R. And you have, so it's elements of this model as G df, or sum of Gi df j, dfi, these kind of sums. And I have relations. This is generators, these are relations. Relations are d of xy, the same relations as written here, is y d of x plus x d of y. Why do we want it? Because this is the Leibniz identity. In particular, you have a natural map from R to Scalar differentials. X goes to dx. And this satisfies Leibniz identity, is a derivation. Was that clear? So it's a formal. So it's a formal.
Definition because you define it by generators.
Yeah, generators are df. This is the general form of such an element in Scalar differentials, and this is the relations. You take a quotient of this free model by these relations, because you want this map to be a derivation. Okay, but as usual in algebra, we have nice functorial definition equivalent to this explicit definition, which is universal property of, it's very similar to how we define tensor product, universal property of Scalar differentials. Yeah, the universal property is the following claim. Suppose you have V, R model, and delta is a derivation from R to V. Then there exists a unique homomorphism from, well, morphism of R models from omega 1 R to, and this derivation, let it be over K, to V, well, omega 1 R to V, which makes this following diagram commutative. You have R, here you have delta, here you have D. This is commutative. So you have two derivations. They are not morphisms of our models, they are derivations, and you have a morphism of our models in the bottom. This is universal property. So there is nothing to prove, essentially, because, look, you have an element of f which goes to V, df. Then this df gives you a generator of omega 1r, and the same element should go to, so let's call this phi, then phi of x, phi of dx, dx is a generator in omega 1r, is equal to delta of x. And this is well defined because this vanishes on these relations, because delta is a derivation. So this is commutative. So you can think of Scalar differentials as a universal derivation So every derivation is factorized through scalar differentials. In particular, this gives you a simple but useful corollary claim, which expresses derivations in terms of scalar differentials. So derivation over k from R to V is equal to hom over R from scalar differentials to V. So it's like a dual, well, if you are interested in vector fields, these are derivations from R to R, then it is dual. So in particular, the derivations from R to R, this is vector fields in quotes. This is same as omega 1 R k dual, because it's morphism to R. So this is intuition, because you should think of scalar differentials as of one forms. And this is vector fields. They are dual. Okay. So now we have to compute something. So exercise omega 1 over k, or, well, k of k1 dot tn is a free model. R, well, R equal to the polynomial ring model generated by dt1 dtn. I suppose I should solve this exercise, unless you really want to. It's not hard. Okay, so let's have a break, and then we shall discuss this. Maybe you can solve it for the time being. 5 minutos interval. let's do this exercise. We have, it's sort of clear by Leibniz rule that this model is generated, so omega 1 of polynomials generated by dt1 over dtn. First, you should notice that differential of 1 is equal to 0. This is because differential of 1 times 1 is equal to 1 differential of 1 plus 1 differential of 1. And this is, so differential of 1 is 0. Just cancel two sides. So since the ring is generated by dti, you apply Leibniz rule, you obtain that it is generated by these guys. And now you need to show that there are no relations. And for that, suppose you have a relation. You just write, you use this isomorphism. And then you notice that inside the derivations, inside the vector fields, you have a vector fields of some sum of fi d per d ti. In particular, and of course, since these two rings are dual, these two models are dual, this means that you cannot have a you have to pair them up, and if you pair them up, you will obtain that the pairing of d by dti dtj is delta ij. So they're equal to 1 if they are so this pairing is equal to 1 if I equal j, and 0 if they are not equal. So the dual model to this model of differentials, of Scalar differentials, is just model of vector fields, which is free, generated by coordinate vector fields. Well, we don't know if it is free generated. Maybe it's not, but at least if you take, well, it is free generated, in fact, because if you have a well, you can check that it is free generated. I won't tell it now, but what is important that they are dual. So if you have something which is some relation between Scalar differentials, so this give you a, this then the map from you would have you won't have a map from Scalar differentials dual to the model R times direct sum of R times d by dti. And this is an isomorphism, this is surjective. So if you have, for that to be surjective, this should be at least free. Can be even bigger, but it can be smaller than field generated by dti. Okay. Well, I didn't tell you the whole story, but it's an exercise. You should finish it yourself. Okay. So if you want to compute Scalar differentials, there are two important exact sequences which are used. They simplify the computations a lot. So the first exact sequence is written here. So you have A quotient by an ideal I is B. So A is a ring, I is an ideal. You have the following funny map. So it is delta takes I to omega 1 A times over A by B. It takes x to dx. Of course, you need to check that it is linear. I mean, otherwise it doesn't make much. So to see that it is linear, you have, if you have d of xy, where y belongs to I and x belongs to A, this is equal to x dy, this is linear, plus y dx. Okay, y dx belongs to I omega 1A. But then this is a quotient, so this model, omega 1A over A times B is equal to omega 1A quotient by I omega 1A. This is something we had a lot. This kind of isomorphism we have all the time, right? This is what we started when we considered tensor product. But then this product belongs to that ideal, so it, after mapping to the tensor product, it goes to 0. This is why delta is linear. Also, delta to I square is 0 because delta, but the same argument. If you have a delta of xy equal to delta of x times y times delta of x plus x delta of y, and they are both in, if they are both in I, then the image goes to 0 under this map. So we obtain a map delta from I quotient by I square. It's a map of models, not derivation, to omega 1A times B. Okay? Was clear? Now we have an exact sequence. Should be probably called, here it's called claim. So you have A is equal to P by I. Then the following sequence is exact. You have I quotient by I square. Delta maps it to omega 1A times B. And then you have, so this is the homomorphism, phi from A to B. So phi maps it to omega 1B. This goes to 0. This is exact. Okay, so let's prove it. There are some things which are entirely obvious. So for instance, this composition vanishes because if you start with, so we already know that d of, so if you have some x in I, it's mapped to dx, but then you apply phi to both sides. So phi takes phi x dy is d phi x, d of is x, it's phi of x, d phi of y, right? And then if y was in I, then d phi of y is 0. So this is why composition of these two maps is 0. And this is surjective by definition, because omega 1b is generated by elements fi dgi, and a to b goes to surjectively, so this is clearly surjective. The only slightly non-trivial is you need to check the kernel of phi is equal. So need to check that kernel of phi is equal to image of delta. This is the only thing which could be considered slightly non-trivial. Okay. Now you have a map omega 1a. I will use the same letter 5 to omega 1b. Its kernel of this phi is equal to, is generated by definition to x dy and y dx, where y belongs to I and x belongs to A. Right? This is the kernel, by definition. So we know how it map X. It just applies phi to both sides. So if something becomes 0, this means that it was in I. Okay. And then, but we already have omega 1a times b over a is equal to omega 1a quotient by I omega 1a. This means that the kernel of this map phi here is generated by elements. So this is already dead by this because we took already a quotient. So it's generated by x dy, where y belongs in I. So this is why the kernel of phi is image of delta. Was that clear? This is sort of standard. Now I will slightly elaborate on that claim by doing a claim which is pretty much the same. Since I'm going to use it, I will call it claim 1. It's so claim 1. Suppose that you have the map phi from A to B, surjective again. B is equal to A quotient by I. And then we'll have also a section denoted here by sigma. Sigma from B to A is a section. In the sense that sigma of phi of sigma of x is equal to x for each x and b. It's usual, the notion of a section. You just have a map which inverts your surjective map. Then this exact sequence is exact on all sides. Then delta is injective. This is what we need to show. Because it's exact, what okay, so let's prove it. I will just use the inversal property to invert this map delta. For that, I will have first I will take a map from rho from A to ideal I quotient by I square. This will be a homomorphism of A models. A model morphism, which takes x to x minus sigma of phi of x. So how it makes sense? Okay, if you apply phi to this, you obtain the same as phi to that. So this is rho. So rho indeed maps to the kernel of phi. This is why it goes there. Well, and then I take quotient by I squared. What is important that rho is derivation. This is really the only non-trivial point in the proof. So it's a simple computation which brings it So first we notice that if you take x minus phi of sigma, sigma phi of x, and multiply it by y minus sigma of phi of y, this is equal to, it belongs to I squared. And since we are interested in the map rho to quotient by I squared, this means that rho of up to I squared, x squared, xy, plus sigma of phi of x, sigma of phi of y is equal to cross terms x, y, sigma of phi of x time plus x, sigma of phi of y. Okay, now we want to, well, mod I square, of course. Now we're interested in checking that this the map rho is a derivation. So for that we take x multiplied by rho of y minus y multiplied by rho of x. It's a sum of 4 terms. Sorry, plus, of course, plus. But 2 of these terms coincide. It's xy. There are 2 times xy here. So this is equal to xy plus, now you have the minus these 2 terms, minus x sigma sigma of phi of y minus y sigma of x of y, sigma of phi of x, right? And now we will express these 2 xy through that using the using this relation. And this would give us, after you write, you just have to put xy and plug, instead of one of this xy, plug this, the rest of these terms here, and it will give you, in the end, xy minus phi, sigma of phi of x, sigma of phi of y. So this is very similar 4-term relations. Essentially, you just bring these 2 guys there, bring this guy there, and you obtain this relation. Okay, but this means that this is precisely that rho is derivation because this is equal to rho of xy, right? Here I use that, again, that sigma and phi are homomorphisms, are ring homomorphisms. So when I tell you about section, I meant that it is a ring section. Section in the sense of having a ring homomorphism there. Was I clear? Clear? No? I can repeat. Should I repeat or what? So again, we want to check that this is equal to that because this is rho of xy, and this is rho of x times rho of y plus y times rho of x. So you put sigma to that term, and they cancel. I mean, xy and 2xy cancel, and then you put this here, and you obtain 4-term relations, which should be 0, and it is 0 by that it's equal to this 4-term relation, which we already have. Okay, so this is a derivation, and this implies that this map actually has a section. So delta has a section. Because by universal property of differentials, by universal property. Okay, so here we actually use that this map vanishes on, well, and since it has a section, well, how section works? Well, it takes x to x. So you have x there, and so it's really a section in the sense that you have this, the corresponding. So this derivation is just rho, but then rho times delta gives you identity, because this is how it is defined on the generators. So rho takes generator x to d to this. And then delta maps it to rho takes an element of I to itself by definition, because phi of I is 0. So this means that rho of on I is identity. And this is why the corresponding. And then delta on elements of I is also identity. It takes elements of I to di. So this means that your composition of this section and delta is identity, and this means that delta is embedding. Okay. This is needed to express, well, you will see on the next slide. So I define Zariski cotangent space. It's a very formal definition, but quite useful, because it's equivalent to the usual cotangent space, even if it is that formal. So you can do it for local rings. You can do it for any ideal. Here I probably define it for local ring. Yeah, you have a local ring, R a local ring, M is maximal ideal. Then M quotient by M squared, this fine-dimensional space over the residue field is called Zariski cotangent space. So the Zariski tangent space is dual, but I'm not going to explain that too much. It's dual to that over the field of residues. I won't use Zariski cotangent spaces on the tangent spaces. Okay, now let me express this Zariski cotangent space explicitly in terms of the well, if you have a Gaussian ring, using this exact sequence which we discussed, it turns out that you can express the Zariski tangent space explicitly. So proposition. You have R a local ring. Then you have R1. Well, you have K is residue field. Then omega 1 R multiplied over R with the residue field is equal to the Zariski cotangent space. This is why I needed these exact sequences, only for that. Okay, so proof. Well, I would use R is equal to A and R1, which is R over M is equal to B. And I would apply this exact sequence. We don't have a section because, well, I assume that it's a local ring over K. So unit times K. So K is embedded there by a vector space generated by unity. So this gives us an exact sequence, which is written there, but it starts from, since it has a section, you have, so this is K, and it's mapped to R. So this exact sequence is exact on all sides. So you have 0 goes to M quotient M square. Delta maps it to omega 1 K over R times R1. And this goes to omega 1 K, which is 0 as we discussed. So if you have a field, the derivations over this field are 0 because delta of 1 is 0. And delta is K-linear. We are considering K-linear derivations since it's K here. Okay, and the same with differentials. So you D1 is equal to D1 times 1 is equal to 1 D1 plus D1 plus 1 D1. So this D1 is 0. Okay, and this implies that M quotient by M squared by delta is isomorphism to omega 1 K R times R quotient by M, which is precisely what we have now. Clear? It's entirely formal. You just apply this exact sequence to obtain this nice description of Scalar differentials. Why do we need it? Then this is because we want to have some inheriting property of, we want to express Scalar differentials of quotient ring from the Scalar differential of a ring and relations. This is possible because we have this exact sequence, and then this gives us a way to describe the Zariski cotangent space of a sub-variety using the Zariski cotangent space of a variety. So there is a corollary which is immediate. So it explains why it is really, well, in a sense it's corollary, but in fact it's very straightforward. So corollary. You have X as a smooth manifold. Have mx ideal of functions. So x is a point vanishing in this point. M squared, this is something we discussed already, is ideal of all functions f such that df restricted to x is 0. This is because of that property, right? So a function belongs to a square of maximal ideal if and only if its scalar differential is 0. In 0, I mean, scalar differential evaluated in your point x. Okay, so this means that you have a natural map differential from from m quotient by m squared to t star of this Zariski cotangent space, and this is an isomorphism. Yeah. It's probably, here I use an tautology, so it's better to say it, well, here we can say it not Zariski, but usual tangent space. Yeah, it's better. So you have a function which vanishes in x. You take its differential. It belongs to m squared if and only if its differential is non-zero. So this is really an isomorphism. This explains why this is a cotangent space. Should I go on? Should be trivial. This result takes work, but this observation has nothing, just trivial observation. Okay. Now I'm going to give a proposition for which is called the Jacobian property of how you can generate the differential, the ring of Kähler, the sheaf of the model of Kähler differentials if you know that your ring is a quotient of polynomial ring by some generators. Okay, so proposition. You have x inside Cn generated, so it's given by is a solution of, so it's a solution given by equations f1 of z is equal to f2 of z is equal to, and so on, is equal to fk is equal to 0. And you have maximal ideal associated with the, so it's f, yeah, so Rx, it's XX written there, but it's in, sort of doesn't make much sense, is a localization of OX, this is a ring of regular function on this variety, in a point X inside X. So we're interested in its Zariski tangent space. And then you can have W. This is in the usual tangent space, T star, cotangent space, T star of X and Cn, generated by df1 dot dfk, restricted to that point. So we consider fi as function, polynomial function on Cn, and we take their differentials in usual sense. Then, and now I have Zariski tangent space, T star X of X is T star Cn by W. Moreover, yes, it was called B. Sorry, it was here. It should be called B. Bx. Bx is localization of OX in X. Bx is regular if and only if the dimension of X is equal to n minus dimension of B. For example, if you have just one equation, then it will be then regularity of X will be equivalent to df X being non-zero. And this is something which we sort of know from the point of view, something we discussed. If you remember, if you have a subvariety given by a set of equations, then it's the differentials of this equation should have should give you a surjective map to the Cn Ck, where you have k equations. If this is true, then we know that the variety is regular by this inverse function theorem, which we discussed 2 lectures ago. So this condition is pretty much the same. It's it gives you linear independence of these differentials, which is the same as the surjectivity of this corresponding differential map to Cn. So this, if we prove this proposition, we really prove that regularity is the same as smoothness. So let's prove it. Am I clear? Okay. So proof. So we have A is a polynomial ring, just the ring of regular functions on Cn. And now B is a, you have ideal I, generated by this F1 dot Fk, and you have B is equal to A quotient by I. So B is OX. I just keep this notation to compare it with what we have before. And now we had this exact sequence. I by I squared goes to omega 1 A over B, times B, goes to omega 1 B, goes to 0. Right? This is the exact sequence we have already discussed a lot. And now we're interested in, mostly we're interested in a maximal ideal of this ring, quotient by its square. So we shall multiply everything by this, by the field associated. So we shall multiply this exact sequence by A quotient by mx. Here we consider mx as ideal in A. It's ideal of this point. Okay. So this gives you omega 1b. Yeah, and if you multiply exact sequence by some model, it remains exact. So the exactness breaks only in the first term, where it is not exact anyway, so it doesn't matter. So it means that omega 1b times over OB or OA, it doesn't matter, or B, B quotient by mx is equal to omega 1a times over A with B quotient by I squared. And this is multiplied by B by mx. Good. But we know what is this. This polynomial ring. So we can just remove this multiplication by B because it's already subsumed in this multiplication. So this is free model generated by D1, dt1, dt2, and so on. And then what is this? This is differential of elements of F, because delta takes F to differential of F. So this is the same space as just T star of Cn. This is space generated by dt1 dot dtn. In the point X, quotient by df1, df2, and so on, dfn, dfk, again in X. So the dimension of this space and this space is, as we have already seen, the Zariski attention space. Dimension of M by M. So it's in B now. It's maximal ideal in B by B squared is equal to dim 2n minus W. This is n. This is n dimensional. This is W dimensional. Okay. So now what is the dimension? So if, so n means dimension of W. If a dimension of W is equal to K, the dimension of W can be a priori less than K. So K, n minus K is, well, you can a priori the dimension, yeah, so okay. So this is the Zariski tangent space. It's n minus dim W dimensional. Then first, yeah, we proved this. This is the first assertion which we had in the beginning. So this T star of x to x is equal to this quotient. This thing is called Jacobian ideal. This is called Jacobian quotient. So it's an ideal generated by, well, you can think of these guys as Jacobians of the corresponding map. Okay. Now, Bx is regular. Regular. If and only if dimension of T star x in X is dimension of X. So dimension of X is bigger or equal than n minus k. Because there are k relations, every time you add a relation, the dimension can decrease, or maybe it doesn't decrease. It depends on, I mean, every time you add the relation, your degree of transcendence can drop. This means that your additional relation is not algebraic over or it can be stay the same if this relation is already algebraic. Okay, and this is a dimension. It's n minus. I mean, dimension of W is this is bigger or equal than n minus dimension of W, because W can be, yeah. Okay, so the equality happens if and only if our ring is regular. Otherwise, it's not regular. And this is what is written there. Okay, so let's do a consequence, and I'm done. So it's just this corollary slightly rewritten. But it is written in such a way that it coincides with this inverse function theorem which we had last time. So you have f1 dot fn, regular functions. So it's polynomials, t1, dot fk, polynomials from t1 dot tk, tn. So corollary. This gives a map, Cn to Ck. F. Then, if x in f minus 1 of 0, so you have level set of 0. This is the set defined by these equations. And df from T tangent space to Cn to tangent space to Ck. Well, to the tangent to 0, actually, because the image is 0, is surjective. Then the point x is regular in this algebraic variety. It's precisely, so this is, we want this space to be k-dimensional where we have k equations. This is precisely surjectivity of this map. But then it is the same statement as we had for smooth varieties. So really, the regularity is algebraic condition, which is equivalent to the geometric condition we had last time about the about the smooth manifolds. When the manifold given by this set of equations is smooth. Okay, I'm done. Thank you very much. And let me show you again the Oh, on the home page of this course, which I cannot get now, it's possible to see the form you need to fill in to get exam problems. Thank you very much. Muito obrigado.